Recording. Recording. Good afternoon, everybody, and welcome to National Careers Week. And today we are so pleased and excited to hear from the School of Engineering from the University of Warwick, and I will hand over.
Hello, everybody. I am Daciana Iliescu. I'm the admissions tutor for the School of Engineering at the University of Warwick. Today's presentation for City and Islington College would present some general aspect of the school, some engineering related careers, some projects that our own students do with links to videos you can watch in your own time. And in addition, we have two other presenters who are researchers in the school undertaking their PhD studies, who will present their own work. So I'm talking here about first year and fourth year projects and also cutting edge research from the postgraduate students in the school. The whole point of basically looking at engineering and doing an engineering degree would be eventually to work in engineering. However, you can have careers not only in engineering, but in other fields as well. And this slide is a presentation of our collaborators, mostly in research, but also in teaching, because those companies have research projects and problem solving with us and also take a number of our graduates, employ a number of our graduates. So my understanding is that perhaps you don't have the idea of what engineering actually means in all its forms, the amount, the depth and the breadth of an engineering career. And that's why I'd like you to talk about some aspects of engineering. Well, first of all, a bit of presentation about the school itself. We are a very well thought after school, the sixth most targeted university for employment for graduates in overall at the university. And the same is true for engineering itself. And we have a number of international and national partners, and about 80% of our research projects contain international partners. So we are very sort of global. We have a sort of global presence in Europe, United States, Asia, Australia, and Africa. So we have global research presence. In terms of careers, basically, if you graduate from an engineering degree, you can do a varied type of job. So, for example, you can work building cars in the automotive sector, and you can recognize here some names, for example, Jaguar Land Rover or Aston Martin. You can work in aerospace. Here you may recognize Rolls-Royce or BAE Systems. However, you can also work on the healthcare or pharmaceutical or biomedical domain. So, for example, AstraZeneca, we have partners with AstraZeneca or DSM. If you want to become a civil engineer, building bridges, houses, plants, here our partner was Balfour Beatty, just as an example. But behind this, you have other possibilities, and you may recognize a few banks here, because engineering has, or gives you a range of skills, transferable skills, problem solving, organization, technical knowledge, which you can take in any other part of your work. In terms of engineering itself, on the left, it's a long list of companies, and they range from civil engineering to general consumer goods with telecommunications, electronics, power, you name it, we've got it, if you like, in terms of engineering fields. You can see what from the pictures a few activities that our students are involved in. So for example, they take measurements, they build industrial rigs, they design all sorts of product or measurement systems. Our school approach is to be a general engineering department, meaning that we combine all those disciplines in a sort of multidisciplinary aspect. So my own discipline, my own stream is electrical and electronic engineering. What this means is for example, our areas, for example, such as communications or connected systems, we call them, devices that through which you can transmit data. And I'm pretty sure that everybody has such a system which they use on a daily basis. My phone just told me that I have spent 3 hours on average per day in the last week on such a device. So this is pure electronics and communication. Those phones also allow me to measure all sorts of things, but of course the whole discipline of sensors and devices is what powers the processing power, for example, of your mobile phone. And last but not least, you need some electrical power to keep your devices alive. And here we are looking into batteries and network grids and renewable energy in terms of power. Perhaps a bit more difficult to explain, but well, more abstract to explain rather than difficult, is the systems and information. Our systems group looks at solving problems in a generic fashion. So if you have an electrical problem or a biological problem or a mechanical problem, the systems discipline brings it together and gives a unified and generic solution. In addition, they look at specific applications, for example, in biomedical and biological systems, and information engineering. So all the things related to artificial intelligence, to smart in front of every single device that you hear about, is a systems and information engineering problem. The other thing that they do is, instead of fabricating initially and basically making a finished product to start with, they start with modeling. So you define mathematically and computationally a problem, and you solve that much cheaply and more in advance of actually committing to full fabrication, and you solve all your problems and troubleshoot that way. And the force control is basically linking all of those components together to obtain seamlessly integrated systems. Then we are talking about civil and environmental engineering. The idea is that all the buildings, the bridges, the infrastructure, which is related to the way we live in our sort of built environment, Of course, water is one of these important aspects as well, and our department has a group looking to solve problems related to the water infrastructure. And of course, we are driven nowadays by aspects of environment and renewable and humanitarian. So those three aspects are basically covered, especially in civil engineering, but also throughout our disciplines. Perhaps the discipline we are mostly known for is mechanical and process, and I must add materials as well. They look at problems of fluid dynamics, measurements and machines. So the whole auto industry and aero industry has its basis in mechanical and process engineering. Now, of course, we need to bring in a lot of materials. So people are also looking at traditional, but also new materials which can withstand different, more challenging conditions of operation. And also because thermal engineering and thermodynamics is also part of the traditional mechanical engineering, we are also looking into the power side, not the transport of the electrical power, but sort of power generation by traditional and new means as well. So by traditional, I mean your power plants, say, based on coal, newer energies, for example, wind turbines. In terms of our numbers, we are a school of about 80 staff and 65 postdoctoral researchers and about 150 postgraduate researchers, two of which you will meet this afternoon. Again, the point of our school is to have a multidisciplinary, collaborative teaching and research.
I had a question. Sorry, I had a question really quickly. As a part of like being a student at University of Warwick, do you have like work placements for students when they're doing their undergraduation, or like industry visit and things like that?
Yes, as part of their degree, everybody has industrial visits as part of the degree. We also have some degrees which are specifically with an intercalated or an integrated year. So in that year, people can actually take leave from the university and work in a real place of work. In addition, we have vacation or holiday placements for our students, which are obviously much shorter and more limited in scope.
And is there like any support that is given from as in a support given from the college, like who will help, like, to get these work placements with companies?
We have a dedicated person for industrial placements, a person who also keeps in touch with students who are away for a year, and then an entire central department which deals with generic placements, with preparing for example, CVs or interviews and so on, for a sort of careers service which is central to the university and which provides also other skills as well.
I see. Thank you very much. Thank you.
You're welcome. Yeah, so this slide will give you two links to our sort of presentation of the department. I'm not going to play them now. Feel free to look on YouTube and watch at your own leisure.
Thank you.
The pictures are a collection of various group projects and different types of applications that we are looking at in the department. So here on the left-hand side, you see a few years ago the Warwick Formula team, and here in the center with the yellow fins is the Warwick submarine.
If I'm not mistaken, that's the Formula Student competition, right?
Exactly.
Yeah, I see. Okay.
Yeah. I also have later a little link to one of the presentations of the Formula Student this year.
Thank you, ma'am.
So our engineering students have start with projects and sort of hands-on from the start. So I will run you through one of the videos that they have presented. In the first year, there are these projects called the sprints. The reason for the sprints is that they are given 3 weeks. So it's a sort of dynamic work package. So they have to apply everything they've learned so far to produce something. So because I am responsible for the electronics sprints, I'll give you a flavor of how the projects, how the students, so remember these are first year students, will present their own projects. So let me play you a bit. I might skip some bit as well when it then becomes too technical, but here it is. Sorry, let me put this a bit lower.
Tatiana, we don't seem to have sound on the video.
Excuse me?
Yeah, there's no sound. Sorry.
Oh.
Sorry.
Right. Then something that let me check to see if I can fix from the this is me running on the sound.
I think when you go to
I need
share
some
content,
help.
when you go to share content, there's a little toggle at the top that says include computer sound. Have you got
Right.
that?
Yes.
If you turn that on and try again, I think that might be it.
Yes, that is it. Thank you very much for the help. Okay, and I'm ready to do now.
The design brief was to make and test a payload to collect data. We were given components and had to create a circuit. Initial design thoughts involved that the mass had to be low for acceleration and the pressure will decrease with altitude.
The department provided an STES D12-5 motor. One motor itself has a mass of 45.7 grams. The motor can provide liftoff as long as the rocket and everything inside of it are less than 283 grams. The payload would have to be of a mass less than 13.1 grams, which we found out to be virtually impossible. In an ideal zero-mass payload situation, the rocket should be able to reach 199 meters max height. At this max height, the pressure rod would would be 99 kilopascals. Flight time for this would be 13 seconds.
This design has each component connected to its own voltage output pin. The pressure sensor and the accelerometer connect to the 5 and 3.3 volt pin, and the SD card is connected to the analog pin, which can be configured to act as output pin using the pin mode function. This design allows us to keep components completely separate.
This concept had the resistor and the buzzer connected to the accelerometer. Everything in this concept is connected to the 5-volt pin, which makes it reliant on the components, so there's more chance of error if the 5-volt pin breaks.
This design has each component connected to its own voltage output pin. The pressure sensor is connected to the 5-volt pin, accelerometer to the 3.3-volt pin, and the SD card is connected to one of the analog pins, which can be configured to act as an output pin using the pin model function. This design allows us to keep the components separate. However, it is not recommended to use analog pins as output pins in close proximity to one another, as it can introduce electrical noise.
This is our concept testing on the breadboard on circuit 1. This is our testing for the breadboard in circuit 2. Our results here did not match our theoretical. And this is our testing on the breadboard for concept 3. This did not give any results and it failed.
The design consists of the Warwick and microcontroller powered by the 9-volt battery connected to the PCB board. The final design is based on the circuit 1 diagram. This is because the outcome of the coding provides the closest value to the gravitational acceleration constant. For the mode, the buzzer is used to finding the payload after landing. We choose the department gave the PCB board over the breadboard because of the lower mass. This one is 52 gram and that one is 99 gram, and the prefabricated PCB board is our choice.
On the far left, we have a 100 ohm resistor. Here we have the MPX4115A pressure sensor, the ADXL335 analog accelerometer, and the KX1205C buzzer. We decided to use an SD card because of the additional size, weight, cost, and coding and noise a transmitter would have added to the circuit. We decided to use pre-made plastic casing in our design to improve the durability of the circuit.
In our final design, we arranged our components efficiently by placing them close to their connections. We corrected an error with the 5-volt pin on the SD card by bridging the gap with solder.
Here's a circuit diagram for concept 1, the final design that we chose. Through the simulation, we were able to change the components to the ones that we used. As you can see, all the wires are connected properly, and this was very useful in our design process, as it laid out the function for each component.
So, as you could see, there was a work undertaken by a group of students who was there to create a payload for a rocket. So each individual person presents their own little bit of the rocket payload, and they work together by complementing skills that they have. From a first-year project to a fourth-year group project, the advantage of a group project in the fourth year is that you have much more specialist engineers. So those projects are much closer to those in industry. I will not be presenting, I will not be playing the videos here, but the links, if you follow them, you can get to each and every one of those projects. So with this saying again, I can open for some of the questions, the floor for some of the questions. If not, I will, if there are no questions, I will hand over to the next speaker.
The barrier to manufacturing in metal is incredibly high.
Do you know how your home is heated? Chances are it's with one of these. Over 80.
Industrial robots have revolutionized manufacturing processes.
Thank you for listening, and you should go and visit our students' YouTube videos to find out more about their project.
Thank you for the presentation, ma'am. It was. I'll forward this to my students, and I'm definitely sure that they'll get a lot of information from this, especially like the ones who are planning to like go to University of Warwickshire. Thank you.
Thank you.
Thank you so much. That was really interesting. And as Sayush said, definitely the videos, if you send us the links, we will certainly share them with all our students who are studying engineering. So that was amazing. So would love to hear from the next presenter. Thank you.
Thank you.
I think I will present next.
Yes, please.
Just a quick addition to Daciana's presentation very quickly. I know Saish just pointed that he asked about the career, the connection between Warwick and industry. So I would just like to add that Warwick also has career fairs very often, very often. So that what happens is that a lot of companies come on site and the students can have a one-on-one interaction with the companies themselves, talk to them, and then obviously the companies, their experts give feedback to the students on their CVs, on their, how they can, secure a job, all of that. And there are also a lot of on-site hirings as well, obviously, for the final year undergrads who want to obviously secure a graduate scheme in all these companies. So all of that is quite Warwick is on hands with that. So I just wanted to add that. From that, I will move on to my presentation. Let me quickly share. I hope you can see the screen now. Okay. Right. So hi everybody, my name is Nohe Saber and I am a PhD student at University of Warwick. And today I will be talking a little bit about my PhD research that I'm conducting at Warwick and a little bit of, insight into the project. So my project is actually characterization and early detection of hydrogen embrittlement in offshore bolts using acoustic emission. And this is a project as a result of partnership between the University of Warwick, the Welding Institute, and Lloyd's Register Foundation. Well, some of the terms in this might be quite new to you, so I will just start my presentation by giving you an introduction about what hydrogen embrittlement really is and what are offshore bolts and how we can use acoustic emission. And then obviously I will relate it to the parts that they play in my project. So to begin with, my project basically deals with a very common industrial problem, which is hydrogen embrittlement. Hydrogen embrittlement is basically a process when a metal becomes brittle or hard and it fails. And this is as a result of a constant absorption of hydrogen within the surface of metal. And what happens is as the hydrogen accumulates in the surface of the metal, it initiates cracks within the structure. And then obviously these cracks will cause the structure to fail. This obviously, harms the toughness of any metal structure that hydrogen embrittlement is taking place within. You can see in the figure 1, there is a there's a crack that has been shown, and it's a very typical crack that initiates on any metal surface that undergoes hydrogen embrittlement. 3 very common conditions that are needed, obviously, is the presence of hydrogen itself, so that it can diffuse within the structures of metal. And then obviously any surface that can take up all of that hydrogen and then allow it to accumulate and initiate those cracks. And then obviously stress as in your material or your structure is under some kind of force or some pressure or any loads, and obviously that initiates all of these factors initiates hydrogen embrittlement. Just on the bottom, figure 2 just shows a bolt, and this bolt has actually fractured, or I can say failed, as a result of hydrogen embrittlement. So as you can see, on its surface, the cracks and the damage that's been done to the surface of the bolt, and that's caused it to fail. So that's a very typical example of what hydrogen embrittlement can do to bolts. And why I have mentioned a bolt here is because obviously my project is particularly talking about hydrogen embrittlement in offshore bolts. Which brings me to the next thing, which is you must be wondering what is offshore or what does an offshore facility really means. So an offshore facility is actually a facility that's situated at sea at some distance from the shore. As you can clearly see in the image, this is a very common offshore facility that's been shown in the image, and that's what my project is about. So my project is about dealing with the bolts that are used within a similar kind of an industry within the sea. As shown in figure 4, you can see all these bolts that are holding this steel structure in place. And these are the bolts, similar kind of bolts that I will be testing in my project for detecting hydrogen embrittlement and cracks. So a very common, it's a very good illustration of what basically what my project is going to be all about. So we're going to be testing similar bolts, and we will put them obviously in the same conditions as they are when they are in service at a similar kind of a offshore facility. The next thing is, obviously I've talked about hydrogen embrittlement and then also how it can occur in bolts and what it does to them. But how will I detect it? The method that I'm using in my project to detect these cracks is acoustic emission. Now, what is acoustic emission? Acoustic emission is actually a phenomena of radiation of acoustic or elastic waves in solids that occur when a material undergoes irreversible changes, like crack formation or plastic deformation or aging of the structures, some temperature gradients, all of those, these factors, some mechanical forces, they all they play a role in the radiation of such emissions. And obviously in my project, I will be using the same technique of detecting these emissions and then obviously using them to relate and locate the points of cracks. A very quick, now I will, after giving you a quick introduction of all these different terms, I will just quickly wrap it around my project and give you an overview of how I will be aiming to do what I've said I will. So my testing would be, I've shown the figure 6 illustrates a rig, the structure that I have designed that I will be using. And as you can see, the bolt that's in the middle is been placed, and then obviously we will put this bolt in similar conditions as it will be when it's in an offshore facility, put it under stress, and then obviously test it and detect obviously hydrogen embrittlement using placing sensors, AE sensors, which are acoustic emission sensors, as you can see in figure 5. So these are the sensors that I will place around this rig and then obviously detect AE waves using these sensors. As Daciana also mentioned in her presentation, that's all electronics part of this project, that obviously we use sensors to detect and then obviously use the data to then obviously develop the methodology that we claim to, that my project obviously is doing so. And then obviously using all of this, I will develop a model that will allow me to look at the remaining useful life of the bolt that is in service. Now, just giving you a very quick overview of what to expect or the kind of signals that are obtained when I will obviously use these sensors, will mount these sensors on this structure, have some radiations, put it under some loads, some forces, compressional forces, and then obviously when I have some data, this is the kind of graph or a similar kind of signal that I should have on my system that's represented through figure 3. And as you can see in figure 4, there's a typical AE setup. Like you can see that there's a crack and then you have an AE transducer that detects it. You've got the preamplifier, amplifier, all of that. So the crack is, when a crack happens, you detect it through a transducer, the signal goes to your system, and obviously you record it and it shows on your screen as you can see. And the signal should look very similar to one in figure 3, which is representing all these different different terms like threshold, amplitude, rise time. I will not go into too much of the detail as it will all be very complicated, but just a quick overview for you to see what a typical AE signal, will look like, and what are its important, properties that we look at when any engineer, looks at the signal on their screens and try to detect some important features in it. So that will be, major part of my project, and I will be detecting these signals when I will be testing my bolts. And that's pretty much it. Many thank you for your time, and any questions, please, you can direct those to me.
I had a question about your test rig. So your entire project is based on like an offshore facility, right? But in your test rig, how do you simulate those offshore conditions?
Right. So as you can see in this rig here, if you can see this rig, the rig is basically, as I indicated when I was talking about it, so the bolt is of the same size. So this bolt will be the same size as I said we have in service bolts, these ones. So we will have the same bolts, but what we will do is we will develop artificial, we will put same pressures or loads on this bolt, that any bolt which is in service in the offshore industry will experience the same loads. So basically I am going to induce those loads and those stress conditions for the bolt that it will experience while it's in the offshore. Basically what you can say is easy way of putting it, replicating it in the lab, if
Now,
that
I
makes
was
sense.
thinking more of the environment, because that's a very high saline environment, like with a lot.
Absolutely. That is also part of the project where we are going to immerse this rig in a sea conditions.
Ah, I
We will
see.
take
Okay,
the same water
I see what you
that
mean.
that's the bolt is going, the same water conditions that this obviously any sea condition has. We're going to take that, replicate that in the lab, and obviously immerse this bolt in that. While the rig obviously the bolt is under stress, we will obviously have it around those same temperature and environment conditions.
I got you now.
Yeah,
Thank you.
no problem. Any other questions?
Yes, I had a question on your research topic, your project. So what made you, how did you come to choose this topic?
Well, when I was doing I did my undergraduate in chemical engineering, and then I did my master's in oil and gas engineering. And when I was doing my master's, since obviously when you do an undergrad, it's a bit more, it's obviously less advanced than your MSc. And MSc is a bit more, a very pinpointed, and it's very particular. You obviously progress further on. And while I was doing my MSc, I really developed that passion and that interest within the offshore industry. And I think it's one industry that really has a lot of scope. So you have a very good window to sort of develop and give to this industry. And I feel like I really do want to build something, and I want my project to, by the end of it, I would hope to develop something that will just change provide an improvement or some improvisation within the industry itself. And for me as an engineer, it's quite empowering, So that's one inspiration for me, that I find it to be quite an inspiration and quite an empowering thing, that you go ahead and make a change in such a big industry like an offshore industry, which obviously is very essential, and the entire world is a consumer, of this industry.
I have to add that engineers are essentially practical problem solvers.
Yeah.
So you need the knowledge in order to tackle those problems, but this is the frame of mind that you will be sort of operating under.
So would you say students after their undergrad, would you say there was a real need for them to go on and do further study and maybe do a master's? Is that essential for them going into some engineering industries?
If I am to answer from this point of view, We have students who graduate after 3 years, and then they work for their employer, and their employer will provide their specialization. We have other students who do 4-year degrees, so they're a bit more specialist. Again, when they go into industry, they will then apply their knowledge and learn further in that particular industry. If you want to do a master's, means you have already decided, if you like, what your specialism will be, and then you get this extra knowledge in a university environment, perhaps with a bit more sort of theoretical bias, but you get that extra specialization. So if you think of our study as a sort of pyramid, the higher you go, the more specialist you become. Therefore, the work or the choices of industries you can work in become slightly more narrower but more focused, in that sense. And if you want to become an academic like us, then you do a PhD, or if you want to work in a research institute, then those research skills, which are a bit extra than the standard sort of undergraduate level, then you will be doing a PhD, and you come up with a unique solution. So if you want unique solutions, more academically rigorous solutions, then you go and do a PhD and specialize even further.
That's amazing. Thank you so much for that. And I know a lot of our students are really striving to get into that industry and hoping to specialize in the future. So hopefully this talk will encourage them to go further on their master's, PhD, and become doctors and come back and teach like Saeed here. So thank you for sharing your PhD study. Shall we move on to Maddie? And then be great to hear about your on, Maddie. So over to you.
All right, thank you so much. Give me a minute, I will try to share my screen. Can you see it? Yeah, wonderful. Okay, so my name is Madi. Hello everyone again. I'm a third-year PhD candidate at Warwick University, and today I will try to give you a very brief explanation and presentation of what research work I'm currently doing. So, well, the topic is basically the structural damage assessment with thermal imagery. So, what it's all about? Well, I'm focusing on a precast concrete buildings. So, what is a precast concrete? It's actually a prefabricated concrete blocks, which are basically delivered on a site and they're assembled together just like a Lego. So you have a very good example that is shown in the top left corner, right? So it's the building that assembles easily just on the spot. So we have lots of examples of a precast concrete buildings that are still exist. And when we talk about the precast concrete, we also need to remember that these buildings were actually constructed the boom of construction it happened right after the Second World War. So back at these days, of course, they were constructed in a very harsh and a very fast manner. And of course, the quality control was not that good. So I will give you just some little statistics about it. Well, it's more or less about my country, but the main idea is actually these buildings, the average age of these buildings is around 55 to 60 years. So they are old and nobody knows what is the current situation with these buildings. And unfortunately, we have some reports that these buildings are already experiencing some, let's say, a major structural issues, like here. We have spellings, we have wall joints destructions, and so on. And we also need to remember that people still live in these buildings. So there are millions of them, and people still live there. and we don't know what's going on with them. All right, so what can actually help us to assess all these buildings and predict what the current situation with them? So we are basically remote sensing can help us. So remote sensing, and in particular the satellite thermal imagery. So the thermal imagery is basically, it's all about the infrared imagery, right? So we all know the example, something like here on the top left corner, right? So basically we have a very hot cup of tea and it shines in thermal camera, yeah, with all reds. But if we will have a look at an example of thermal image from the satellite of some area, and right now this is an example actually of Sacramento, so it's somewhere in the US. So as you can see, on the left side is basically just ordinary optical camera, an image from the top, from the space, and on the right side we have the same place but taking a picture from the thermal camera. So the buildings that emit more heat, they are basically highlighted with the red. Okay, so this all just give us an idea about few things, right? That buildings that emit more energy, that they have lower insulation. And at some point we've come an idea like, what if the buildings that actually emits more energy, more heat energy, right, to surrounding, what if they actually experience damage and progressive damage? Okay, so here actually where my project is actually start from. So we've made an idea that actually the buildings that actually experience the progressive damage, it's actually the heat leakage for these buildings is getting higher and higher from year to year. Okay, so here is on the screen you can actually see the damage assessment tool. It's a graph of how the whole process works. So basically we take an image over several years of the same place for the several years, let's say 5 years, 10 years, well, as more as better. And we check the heat emission of every single building and compare them with each other. Of course, when you have only 10 buildings, right, it's very easy actually to make a comparison. But then if we're talking about, let's say, an area of a city size, or let's say like 2 cities size, right, or let's say a London size, it's a really huge. We have millions buildings over there. And of course, the first thing what comes into to your mind is actually, the first difficulty is actually to find which of all of these buildings are precast concrete buildings. Right, and the second thing, you also need to try to calculate all of them, and then make an automatic system that will actually make all these comparisons. All right, so here what it comes, another difficulty. So it's basically about the image qualities. So on the left side, you can see the multispectral image is basically what the thermal camera is giving to you. And out of this, it's very low resolution image, right? We need to receive something like this on the right. So we should actually be able to understand where the building are, right? So this is a process of punch sharpening that we're actually dealing with. All right, after we receive all the very high resolution images, but yet they are still of a different color. And as you can see, let's say here this one is more greenish, this one is more bluish, right? We need to make them more or less equal to each other, right? So then we can actually make a comparison between apples and apples. This is where histogram matching helps us. All right, and then we actually implementing the deep learning techniques of object detection. Well, I'm not going to tell you into deep like what actually the deep learning is, but it's actually a type of algorithm that simulates the work of a brain cell. It's very handy, it's very useful, very powerful, but it's actually has some restrictions, and especially about the quality of data. All right, so this is an example of what I'm dealing with. It's a YOLO object detection algorithm. It wasn't developed by me. It was actually Joseph Redman and Ali Farhadi from University of Washington. They developed it, and since they are computer IT engineers, and I'm a civil engineer, so It's not my area of expertise, so I'm just using their work. But this is what I have. It's basically the algorithm detects the buildings, right? And it helps us, it helps me actually to be able to produce a damage classification maps. So as you can see, it's already an outcome of the whole process, what we have done through, what we have gone through. And as you can see here, we have some green buildings, which is more or less, we can say they are fine. We have yellow buildings that we can try to say that, yeah, there might be something wrong with them. And there are red buildings, which highlights to us there are definitely some problem with them. So in particular, let's have a look on the building, this one on the right, which is highlighted with red. Yeah, this is a closer look, right? So as you can see, we've done a testing for the year 15, 16, 17, and 18, right? So and the bottom left corner is actually having some progressive light, the heat leakage intensity. It's progressive heat leakage intensity throughout the 4 years. All right, so it just gave us an idea, right? There might be something wrong with this building. So we went to a spot and checked the building, right? So here it is on the right side. And as you can see, it has all the major crackings, and especially with the joints. The building itself, it looks like this. And if you will look at through the thermal camera, right, it just highlighted with all the reddish and yellowish, which is just give us an idea that this building is basically emits a lot of heat to surrounding. Which is comparing to other building, let's say C1 is a low critical building, right? C3 is a critical building, C1 is a low critical building, is completely, totally different situation, right? Okay, so this is how the whole process works. And this is another closer look. So as you can see, we have some cracks over here, and it is highlighted with all the whites. So the white is like the most intensive heat leakage. This is all as a given idea, right, that this building having a major problems. And basically, this is how we not saying decided, but this is our proposal, how this problem of a massive damage assessment of this particular type of buildings can be done. All right, this is pretty much it. Well, thank you very much. And if you have any questions, I'll be very happy to answer them.
So basically, for your project, you constantly monitor the thermal imaging of one area, like over a period of time, right? So
yes, well, not a bit, not exactly like what you said. I'm not monitoring at only one spot. So the idea of this damage assessment tool is actually you can use any data and it will give you some results. So in terms of data, it's basically you can take any area in the world but the only thing you need to know is basically it's designed that it's only can be applicable for the countries when you have 4 seasons, when you have a cold winter. Because during the winter, you have a heating system that works, right?
Yeah.
And this is where you have the heat leakages. Of course, during the summertime, there is no point actually to measure any heat leakage.
It's quite interesting to look at this, like just looking at a thermal camera. Yeah, it's quite nice, your project.
Well, thank you so much. Well, this is only the first part what I've currently done. Well, the results of this work is I've already applied to a journal, trying to just submitted my manuscript to have my first published paper.
I had another question, like, do our current satellite systems, do they have like infrared capabilities? Like, how easy is it to get an infrared image of any given area?
It's actually, well, you can get some free images, definitely. But, the operating thing about these satellites is actually very expensive. And of course, the company who owns these satellites, they will definitely charge you some money.
Yeah.
Yeah, so you will. So the only thing particular to these images, I had not saying the connection, but I had to speak with it's a government company, so I had to speak with them, and I just convinced them that the most the outcomes of this work may actually contribute to the whole society, because there are millions of people living in these buildings. So definitely they came forward to me and they said, yes, we're going to give it to you, this data to you. But there was again some restrictions. They couldn't give me like the whole city, because of course on a city you will have some secret places, right? That
true,
nobody
true.
needs to know. And I had also to sign all these confidential agreements,
I
so I'm
see.
not gonna share it with anyone else.
Thank you so much for your project overview.
Oh, thank you.
Yeah, this was, this was so interesting. I think the moment I saw the flat packed house coming up, I thought, oh, I want one of those. I could do with one of those and just, ship it to Africa and put it up, and then, there we go. And obviously with the climate in Africa, losing heat won't be a problem, but I'm sure we'll have insects instead and bits and bobs coming in. So thank you for that. And I wish you and Sabir all the best with the rest of your research project, and I hope it goes well.
Thank you.
Same here.
So I think if there's no more questions, because we have come to the end of the session now. So I want to thank everyone for presenting and taking your time to share your data and your insight to our students. I just want to end by just asking each of Maddie and Sabir what if you can give our students a piece of advice, what advice will you give them in terms of progressing, um, right from making their choices to the process to when they're actually on the course, so they can make a smooth transition from college onto their university course?
Right. Should I go first? Right. One very, very golden piece of advice from my side, being a student, myself. The first thing that a student needs to do, especially from a student who's at this level, at a college level, where obviously they're going to start, their journey with their undergraduate, is to plan beforehand. They need to be well planned and well thought out in their ideas or their mindset, in sense that they need to start. We feel like students feel like, oh, I have a lot of time and I can get this sorted later on, but you need to be sorted from day one. So you need to know you should target the universities that you want to apply to, check their websites, talk to their staff, visit their careers. They're like, they have open, I think, open house days. Go visit them, have a night, have a feel of it, because it's very, it's a very big decision. So you have to be all in and you have to be very well prepared for it. So my advice would be do your research and have a background knowledge. So you need to know, whatever, whether it's engineering or any other field that they want to apply to, they have to make sure it's the right universities that they're applying to, right programs, and they've got the right image in their mind. So that's the most essential thing and the best advice I think I could give to them as a student. I suffered from it, so where, if I could go back, I would make a lot of changes. But yeah, I would want the students not to make the same mistake as us.
Thank you so much for that. I have to go to another meeting. It was really great to meet all of you. And thank you so much for your advice as well. Thank you. Anyways,
Thank
take
you.
care, everyone.
Thank you very
All the
much
best
for
to the both.
organizing.
Thanks. All the best to both of you for your PhD. Cheers.
Thank you. Thank you so much.
And Maddie, what if you have any advice to add to the students as we are recording?
Well, I'm 100% agree with what Nahes just said, and I can only add that, yeah, guys, you have to start creating as fast as possible, as soon as possible. Well, as sooner you will start actually creating some stuff. When I'm actually saying the creating, it's basically developing your skills, is getting your knowledge and trying to build something that you can actually touch. As sooner you will understand what field of knowledge you are more interested in. what field of, not saying industry, but of a science you are most interested in. And this is the time when you actually make a real mature decision. What is your future goals and what subject you want to study further? All right, this is the only advice I want to say, especially at this moment.
Great. Thank you so much for everything. And here at the college, the students they know where we are. So any students who are watching this and who are not sure, we are based in so the Career Centre is in a sixth form block. And it's L27. So that's our location. You can drop in at any point and come and speak to careers about all the wonderful pathways and branches of engineering that's out there. But it's definitely really good advice in terms of doing research early and knowing all the different areas of engineering so you can make an informed choice. You know, we have some students who maybe hear a certain type of engineering and they would go with that one without doing their research. So, you know, my advice also to students is do your research, know all the range of engineering, and then just go with the one you think is going to be best for you. So we will close now. And as I've said lots of times, thank you everyone for being here today and participating. And we look forward to sharing your slides with our students. So it will be on our YouTube page and we do monitor the views on there. And Sayush will ensure that the other engineer teachers will play it inside their lesson at some point. Thank you very much.
Thank
Bye.
you.
Thank you for organizing this. Thank you. Bye.
Bye. Goodbye.